So the focus of today's talk is knowing the unknown unknown for safe artificial intelligence. So let's start with an application where we have a full autonomous system. Right? So we have these self-driving cars. They can detect objects and move forward. If you are in one of these self-driving cars, you don't want this to happen. Unfortunately, these kind of accidents are common. Our objective is to build safe autonomous systems. My agenda for today is I'll give you an introduction, an overview with a focus on uncertainty and focus on 3 different applications in a very high level. OK, so we want to build safe autonomous systems. When we think about safe autonomous systems, there are 2 parts: modeling and decision making. We gather data from various sensors, such as camera, LiDAR, GPS, and we build a model of the environment. And we use that model for decision making. In this case, the blue car might decide to change the lane to left. And specifically, I work on uncertainty at the intersection of modeling and decision making. When I say uncertainty, the models that we develop output uncertainty. When we have that uncertainty, the decision-making algorithm can explore various scenarios, whether to switch the lane to left, right, or go straight. Then make the best decision. When I say the best decision, it's always a trade-off between safety, efficiency, and other factors. So when I say uncertainty, there are 2 types of uncertainties: epistemic uncertainty and the aleatoric uncertainty. Aleatoric uncertainty is also known as the known unknowns. And the epistemic uncertainty, in more layman terms, is known as the unknown unknowns. Let me quickly explain what these 2 terms are. So consider we have this blue car, and it has a LiDAR sensor that can measure the distance to nearby vehicles. This is how the blue car would see its surrounding. It's just a point cloud. Now, if there's a vehicle in front of that, we can compute the bounding box. Right? But if we take repeated measurements, we are not going to get the same bounding box. It would be slightly different because of the inherent uncertainty of the measurement system. This inherent uncertainty is common for any measurement system. So that is the aleatoric uncertainty. Epistemic uncertainty is slightly different. So if we have something in front of us, what is behind that thing is occluded, and we do not know anything about that area. So this red area is the epistemic uncertainty. So there could be a car there, or it could be a truck. And if we mistake a car to a truck, that is going to be catastrophic. So in a one-dimensional example, I'll quickly explain what these 2 terms are. When we make measurements, there is some noise. That uncertainty is the aleatoric uncertainty. And in areas where we do not have data, that is where we have the epistemic uncertainty. Quantifying this epistemic uncertainty is hard. But it is extremely important, because it is OK we do not know something, but at least we should know that we do not know about it. And if we do not consider epistemic uncertainty, we would end up in this kind of tragic accidents. Let me show you another example. This is a Mars rover. In Mars exploration, what we are trying to do is we send this rover to Mars, and it will build a map of Mars. And what you see here is a boulder on Mars. And we want to learn the function f of x. X are basically some locations. Given the locations, we want to learn the elevation. Because we are interested in uncertainty, we not only want to model the mean elevation, but we also want the variance of the elevation. Variance is the uncertainty. Right. Now, we can build this kind of models, and we can get the mean and variance maps. But if we look what is behind this boulder, it's a huge pit. Right? We can see in the mean map, it's a huge pit. But because we estimate the uncertainty, we can avoid that pit. So now the Mars rover would avoid that pit. Otherwise, it would fall into the pit if we do not consider that uncertainty. Right? If it fall into the pit, it would cost billions of dollars for the entire Mars mission. So in this kind of high-stake and safety-critical task, estimating the epistemic uncertainty is extremely important. Now, I talked about the importance of estimating the epistemic uncertainty. Now, let's quickly see how to estimate that. Now, in the simple linear model, y equals wx, if you want to estimate the epistemic uncertainty, we have to introduce probability distributions over the parameters of the model. For instance, I introduce probability distributions over the weights. Because we have probability distributions over the weight, now my output is also a probability distribution. Now, this is the same even for neural networks. If you want to get the epistemic uncertainty, we have to introduce parameters over the probability distributions over the parameters so that we will get a probabilistic output. In order to estimate these parameters, we have to use the Bayes theorem. And for complex model, computing the posterior of this Bayes model, posterior of this model is not tractable. Therefore, we have to resort to approximate Bayesian computation techniques such as Laplace approximation, variational inference, MCMC, and so on. Now, there are plenty of applications of these approximate Bayesian computation techniques, and we have worked on trying to predict the epistemic uncertainty of occupancy, directions, velocity, and trying to predict the uncertainty when we are trying to predict something ahead, like future predictions. Now, today's talk is not going to be about approximate Bayesian inference because there are plenty of applications, but we are specifically looking at alternatives to estimate epistemic uncertainty. Now, the general field of dealing with this epistemic uncertainty is called epistemology in philosophy. Let's start with a cartoon. So we have this stationary car, and there are two pedestrians. And the question that we are interested in is a given position free or occupied? Say this position. Now, in the first scenario, the second pedestrian is occluded by the first pedestrian. So we have lack of information. It could be free or it could be occupied. Now consider the second scenario. We are looking at a different position. In that position, clearly, that position is occupied because there's a pedestrian. But if we move that pedestrian to a different place, now that place becomes free, right? So within a given time interval, that position is free and occupied, right? So now we have conflicting information. And when we have lack of information and conflicting information, uncertainty arises from various sources. And typically, Bayesian inference is not really good at handling that kind of situation. So we can use something like evidence theory, also known as Dempster-Shafer theory. I'm not going to discuss all the theory behind this, but I will show you several applications where we have used Dempster-Shafer theory. The first one is spatiotemporal environmental prediction. So what you see here is a self-driving car, and at the bottom, the occupancy map. An occupancy map shows which areas of the environment is occupied and which areas are free. Red indicates occupied, like buildings, and blue indicates driveways where we can actually drive. It's free areas. Now, Itkin has developed this model based on Dempster-Shafer theory, and in today's talk, we are going to discuss how to predict into the future with this kind of maps. So our objective is, given a set of past maps, can we predict how the future would look like? Now, this is very natural, right? When we are driving, we are always trying to predict what will happen in the future, and that's how we make safe decisions. The key here is, given a set of maps, we divide the environment into static and dynamic. We call it prongs here. Right? A static environment contains static objects like buildings, trees, and the dynamic maps contains moving vehicles and pedestrians. And we try to predict each each map separately using this PredNet architecture. And finally, we have data coming from 2 different sources, and we had to combine that, and we use the Dempster-Shaper update rule for that. And at the end, we can generate future maps. So we use this Waymo data set for evaluation, and this is one of the scenarios, a vehicle turning at a 4-way intersection. We consider 0.4 seconds into the past, and now we are going to predict into the future. We are going to predict 1.5 seconds into the future, and with our method, we can show that we can improve the prediction accuracy as well as reduce object disappearance. So just to conclude this section, we have developed a double-pronged convolutional LSTM architecture for predicting future occupancy maps with the help of evidence theory. Let me jump into the second part, multimodality in deep latent models. When I say multimodality, I'm talking about like multiple possible outcomes. Now, we have all these really complicated, sophisticated deep neural networks. This is a variational autoencoder that is used for trajectory prediction. Can we specify the latent vectors of these variational autoencoders? Right? Because if we specify them, that actually helps with interpretability, as well as it helps with downstream tasks such as control and planning. So this is a variational autoencoder. If we input, say, an image, it should be able to reconstruct the same image. And at test time, if we sample from this latent space, we can generate various numbers. In a conditional variational autoencoder, in addition to the encoder and the decoder, there's this conditioning network as the input. What we are going to say is, hey, generate only even numbers. So it will generate 0, 2, 4, 8, and so on. The latent space of these conditional variational autoencoders is generally continuous. But here we are specifically interested in discrete latent spaces, such as Bernoulli or categorical distributions. Because discrete latent spaces help with interpretability. Because what we have here is a code when we have discrete latent spaces. Also, there are plenty of applications in natural language processing, graph learning, and multimodal predictions. So when you have these conditional variational autoencoders, the last layer of each input network is a normalization, softmax normalization function. But the main problem with this softmax normalization is softmax does not produce sparse distributions. Let me quickly try to explain what that means. So we have this conditional variational autoencoder with 10 latent classes, and I'm asking it to generate even numbers, only even numbers. And we can see here like 0, 1, 2, up to 9, and all the probability distribution, like the probability distribution is like spread everywhere. So we came up with this alternative to softmax called evidential softmax that is based on evidence theory. We can compare the two, and here we can see 0, 2, 4, so on. We have this multimodal distribution, and it is almost uniform for even numbers. Also, we compared with various other normalization techniques, sparsemax and nmax, and we can see that our method, the green one, does not collapse into one mode, as in this one. It's equally spreaded. And then we extended this to these complex networks, such as Trajectron++, so that we can, in this case, like this kind of a trajectory prediction, we can get possible modes, like different modes, whether to go left, right, or straight, and so on. Just to conclude this section, we can use L-softmax as a sparse multimodal alternative to softmax. Now let's look at a slightly different example, out of distribution detection for automotive perception. So we have this self-driving car, and can it detect this kangaroo? This actually happened to Volvo. For their they could not actually detect this the kangaroo. Let's quickly analyze the scenario. Now, for the classifier to detect these kangaroos was trained using data obtained using from, say, North America or Europe, where there are deer, human, and car. But when they try to deploy it in Australia, there are kangaroos. Right? The network has never seen kangaroos. So that is what we call an out-of-distribution sample. How do a classifier identify things that it has never seen? There are two ways to go about this. We can have implicit models, such as Bayesian neural networks. If you use a Bayesian neural network, it will provide you a confidence or uncertainty that you can use to detect OOD, or out of distribution. Now, here we are looking at dedicated methods. For instance, we can input some images of kangaroos and train the neural network. But we cannot really do this for automotive applications because there are so many different scenarios or events for out of distribution. Let's look at the classifier. We have this classifier C. It gets some data and outputs some labels, basically some probabilities. And we are trying to minimize this loss, LC. The problem here is, even if whether we input a deer or a kangaroo, it will get very confident answers. Right? But instead, what we want is, if it has not seen a kangaroo, we want every class to be equally possible, a uniform distribution. That is the desired output. Just to revise, the objective is giving the classifier the ability to detect out-of-distribution samples. But the problem is, if the classifier has never seen all these samples, it can't learn how to differentiate them. One of the solutions is to generate some out-of-distribution samples from a generative adversarial network and then train the classifier. So a generative adversarial network has two parts, a generator and a discriminator. What we are trying to do here is, using the generator, we are trying to generate some out-of-distribution samples. OK, now we have a GAN and a classifier. Let's combine them as in Li et al. This is the combined network. We can see the equations are very similar, and we have the GAN part as well as we have the classifier part. Right? But in addition to that, we have this extra arrow. This is where we try to do that trick where we try to get this uniform distribution. We add this extra term to the classifier that would encourage coming up with this kind of a uniform distribution when we input OOD data. Okay. Let's focus on the classifier a little bit. Rather than having all three classes, let me consider two classes, red and blue, and just two features for demonstration purposes. When we train a neural network, we will have this classification boundaries, decision boundaries. Right? What we are actually doing here is we are artificially introducing these out-of-distribution samples shown in black so that our classification boundary would shrink. So these OOD samples, they need not to be anything interpretable, because we cannot really generate a kangaroo without seeing a kangaroo. Right? Even though they are uninterpretable or something meaningless, still we can shrink the boundary. And with this, we can look at the classifier into more details. Last layer of the classifier is a softmax that converts logits into probabilities. And we can compute some statistics post hoc, like after training, for each class. So different classes will have these different probability distributions. And when we get a new sample, we can compute the distance from each probability distribution. And we can show that it follows a chi-square distribution. And from that, we can compute whether we can decide whether a sample is OOD or not. And we conducted experiments on new scenes, Kitty, and various data sets. And when you use new scenes data set, which was trained on Boston and which was collected from Boston and Singapore, compared to some other baselines, we can detect OOD samples. For instance, these horse carriages are common in Austria, but not in Boston and Singapore. So our method would detect that is out of distribution. To summarize this section, we can generate OOD samples from a generative adversarial network for training a classifier, and then compute post-hoc statistics for detecting OOD at test time. So the key takeaways are the epistemic uncertainty is important for safe AI, and predicting into the future and distinguishing lack of information from conflicting information is also important for safe AI. And looking at multiple possibilities or multimodality, as well as latent space interpretability, helps safe AI. And detecting OOD samples is important because we can then trigger safe fallback modes. So detecting epistemic uncertainty and quantifying epistemic uncertainty is extremely important for safe AI, although it is hard if we really want to use safe artificial intelligence systems in the real world. We might have to look at how to quantify epistemic uncertainty. Thank you. And I would like to give a shout out to all the students who work really, really hard to get all these results.
Thank you, Ranslu. Any questions?
Thanks for your talk, Ranslu. I was wondering if you could talk just a little bit more about the notion of out-of-distribution-ness that you're trying to capture with the GAN-generated images, because presumably aren't they like encouraged to be close to the real training examples?
Right. Let me go back really quickly. Yeah. So what the generator tries to do is like it's trying to generate some images that look real. Okay. The notion is it's look real. But what we want here, because of this extra term that we add this not only to the classifier, but also to the generator. Right? Because now the generator will try to generate, it will encourage generating some out-of-distribution samples so that it would be flat here as well. It's not like the PO generator, but we have this extra additional term.
Yeah, thank you for the talk, Ranslu. This may be a little naive of a question, but have you considered encouraging an OOD class itself instead of, bounding everything to be uniform across the existing classes?
Right. So if you consider it as a separate class, now the classifier would take it as like a supervised, it is supervised learning, right? So we might need data from all possible scenarios. Now in this kind of automotive applications, we might need, kangaroos, and if you go to a different country, a different animal, like to train that, we might need more realistic data.
I guess it's the problem itself.
Yeah,
you're saying.
exactly.
That is the problem.
Yeah.
So it was naive. Thank you.
Yeah.
I have a question, Ranslu. So when you're doing the occupancy grid, if I'm understanding that correctly, you're kind of doing direct predictions on the future state of each grid point. Is that correct? And I was wondering how that technique would compare to a slightly more explicit technique where you say try to identify the objects in the scene, understand that they're occluding then the things behind it, and try to capture the epistemic uncertainty in that way.
Oh, right. So you mean like the second part, right? The spatial temporal prediction. Is that what you were talking about? Or? Yeah. So yeah, there are two ways to go about this. You can have explicit trackers and try to predict, or you can try to predict the entire environment at once. Now, the good thing about trying to predict the entire environment at once is that you can consider all the interactions are kind of embedded, right? Now, because it does not have these unique objects, but everything is embedded in the system, and they will interact with each other. And that's why we think trying to predict the environment is at once might be a good idea.
Gotcha, thank you. Okay, let's thank Ranslu.